Hey Arbitrary, what's up? Wow, insane. Crow. Look at that. Coming in. Oh, it's 9:31. What am I doing? Oh, that's a good question. What am I teaching today? Ah, that's right. Teaching rings. New topic. That's right, folks. We're switching topics. Moving on with the semester. Because the semester is supposed to... 44 minutes. That's right, AC. At 44 minutes now. To teach the same amount of material as normal class. Insane. Yeah. So the class is supposed to cover traditional topics in group theory, which is code word for get to the Silo theorems and then get the hell out of there after that, which we did. I think the last homework assignment, the one that's happening right now, that's due today, I want to say it was a good idea. Based on Discord chatter, I think it was a pretty educational experience. So I feel like the students are pulling the levers of group theory to the ability that I hope for. So we will see more group theory definitely next semester when we do Galois theory. That's half of Galois theory. So it's not like it's over. It's not like you should let it go away, escape your brain or anything. But we do have to move to the next topic because we have like a month and change left. So that's what we're gonna do. 2 teachers' pets. I forgot to change that. Okay, let's go. Rings. I'm going to start with examples of rings, and then I will attempt to write the definition. And there will be some controversy. This will be really controversial. Okay? So that's where the clickbait YouTube title will come from. All right. Awesome. Okay, so examples. Let's start with examples. So the first thing I want to say to you, class, is you know a ring when you see one. Because what a ring is in slang, a ring is a thing that has 2 notions. A notion of adding and a notion of multiplying. That obey the distributive law. That's just the bottom line. Okay? In slang terms, a ring is a thing with a plus operation and times operation, which these operations, they communicate well with each other, like you're used to with like distributive law and stuff. Okay, so let me show you a bunch of examples. Let me show you a bunch of examples of rings. All right, I'm gonna go through a list of examples. The sort of prototypical primordial example, the example. The integers. With addition and times as the two operations that create the ring structure. Okay? Primordial example. Another example. Z mod 6Z. The plus and the times in remainder mathematics. Oh, sorry, that's called modular arithmetic. Sorry, I just make up other words for things. But it is the math of remainders, right? When you're dividing by 6. Okay, that's a ring. Let me show you another ring. 2x2 matrices. 2x2 matrices with integer entries. No condition on invertible or not. All of them. With addition of matrices and matrix multiplication. Okay. Kappa has decided to type something important in the chat. Kappa writes, 1 ring to rule them all, 1 ring to find them, 1 ring to bring them all, and in the darkness bind them. Thank you for participating in class. Okay, next example. Q. It's the fractions. Oh, that's called rational numbers. Adding fractions and multiplying fractions. So this addition is from 3rd grade. And this is from 4th grade? I forget. I don't know. Okay? That's a ring. Example. All right. R. R is a ring. Real numbers. Set of real numbers, which I don't know if you've ever seen it defined, but you should ask, what the heck is a real number? But you know, it's like pi and pi square root of 2e I plus e plus the square root of 2. But like, what are all of them? Got to take a real analysis course before you can understand how to define the real numbers. But let's pretend we know. You know, it's what you think it is. All right, example. What's the plus and the times? Exactly, Kappa. All the sizes of pieces of cakes. All conceivable sizes of cakes. Pretend atoms are infinitely divisible. Oh my god, what is a real number? Okay, next. I'm having an existential crisis. Let's just not go there. We know what it is when we see it. All right, complex numbers. This part is complex number math. All right? You can write it out. A plus bi times c plus di. Define it like that. Okay? Do that. Here's an example. 3 by 3 matrices with complex entries. Have you ever tried that before? Okay? All right. Global sections, but algebraically challenged. Which sheaf? Global sections of which sheaf? Structure sheaf? Yes, it's a ring. Okay. Okay, good. 42 plus 42i. Osho. Osho with the meaning of life plus I times the meaning of life. Good one. Let me write that one down. Osho has a Netflix series about them called A Wild Wild Country. Highly recommend. Okay. But let's do Osho's example. Integers plus integers times I. This ring has a name. It's called the Gaussian integers. All right? How do you add and multiply? This complex number arithmetic. One might say that this is a subring of the complex numbers. One might say that, and one would be right. Okay? Good. Let me do another example. I'm just gonna make up an example real fast. You take all the numbers of the form integer plus an integer times square root of 2. Yeah, I'm just starting to list all of them. It's gonna take too long to list them all, so I'll stop. Okay? How do you multiply? FOIL. Collect terms. How do you add? Add. Okay? So, all kinds of rings in this world. This world is filled with all kinds of rings. Let me read the Wikipedia. Let's go. You know what? Let's see what Wikipedia has to say about rings. Let's do this. This is a good thing to do, students. So Wikipedia. I googled Wikipedia, then I clicked on the link called Wikipedia, and then I clicked ring. Okay. Ring most commonly refers either to a hollow circular shape or to a high-pitched sound. Wait, hold on. That's not the right one. There we go. There we go. Found it. Found it. In mathematics, a ring is one of the fundamental algebraic structures used in abstract algebra. No. No. It's not just used in abstract algebra. It's part of the veins, the xylem of the tree of mathematics. It's not just abstract algebra. It's like knowing what a number is, or groups. Groups are everywhere. It's not just abstract algebra. Yeah, rings, they're everywhere. They've got this big Z as a picture of a ring. Amazing. Okay? So we know a ring when we see one. And now? Okay, and now what I'm going to do is tell you I'm going to attempt to tell you the definition. Definition. And then you look back at the examples and it'll all make sense. Oh, okay, yeah. Definition. Okay. Let's go. A ring. So one thing I should say before this. You stop any mathematician on the street and you ask them for the definition of a ring, they will fail. Because there's actually a little bit of controversy what to include and what not to. And maybe you missed some of the axioms. Okay, but you know it when you see it, all right? So I'm going to try it. A ring is a set R equipped with two binary operations. First one denoted plus, and the second one denoted dot. For us, okay, I'm just giving a name for them. Two binary operations. What's a binary operation? It's an operation that takes two elements and outputs another element in the ring, in the set. Okay, so ring. This ring is a set R equipped with two binary operations, such that. Now I gotta do axioms. Okay, how? Help me. Oh boy. Okay, I can do one really easily. Plus makes R into an abelian group. So the plus operation makes R an abelian group. That's fine. So A plus B is B plus A. There's some identity element called 0. We denote 0 is how we denote the identity operation. Identity element. Am I saying 0 is a number like 0 apples? 0 apples. The concept of 0 apples is present in every single ring. No, I'm just saying that let's call the identity element 0. Let's just use the symbol 0. That's it. Symbol. It's a symbol. Computer doesn't know apples. Okay. Number 1. The plus operation, abelian group. 0 is the name of the additive identity. Okay, number 2. Okay, this is going to be called addition. Just words. Addition. And this is going to be called the ring multiplication. Right, number 2. No, we're not going to use the opposite words. Chat is getting weird. Okay. Okay. 2. Multiplication is associative. So like this. Multiplication is associative. All right. 3. It's called the distributive law. It says A times B plus C is and on the other side too. Okay? This axiom tells you how the two operations communicate, mix. It's very essential that you have distributive axiom. Okay? Otherwise, you just have two operations and you don't know how they kind of combine together. Okay, so this links them. Very important. 4. And this is controversial. 4. There exists a multiplicative identity. Again, symbol. We're just gonna use the symbol 1. Just Just some concept. 1. Okay. There exists an element 1 such that 1 times A equals A times 1 equals A. Okay? Existence of a multiplicative unit. Okay. So I'm going to say that I did it. I think I got the axioms right. This is what a ring is. It is a set with 2 operations plus dot. Plus is just an abelian group structure. And then dot is some new thing. It's an associative thing. And it combines with plus according to distributive rule. And then there's a 1 for the multiplication rule. That 1 times anything is itself. Wait. Wait, composition? Hold on. Kappa, Hilbert space, plus and composition, that has an identity. That has an identity. Now, convolution product. Oh, if you put that. Okay, yeah. Yeah. Okay. So there's some controversy here. Yeah. Okay. So here's the deal, class. So what is Kappa saying? There's actually a choice that has to be made. There's sort of a debate. Should the multiplicative unit, multiplicative identity, multiplicative identity, should the 4 be included? Okay, so if you ask someone who's like me, who does a lot of like commutative algebra related things and algebraic geometry and so on, number theory, you know, the place where rings really came from historically. Every one of our rings has a multiplicative identity. Okay? So we will default and say rings should have multiplicative identity. And you get these weirdos like Kappa who talk about Hilbert space and convolution product and all this garbage. Unfortunately, those structures have everything except a multiplicative identity. I'll give you a much simpler example. Here's a much simpler example to consider. Is 2 times z. With plus and dot, the usual, first grade. Is this a ring? According to that definition up there, no, because there's no element which serves as multiplicative identity. No. 4 is not holding. All right, so 4 doesn't hold. So that's an example where this definition doesn't include something that maybe you would want to call a ring. Okay. Then there are people who say rings have to have an element like 1 or an element that's multiplicative unit, identity. Okay. Then there's the other camp that says, no, forget that thing and do the more general thing. All right, so what we're going to do is we're going to assume that our rings have multiplicative identity. So I'm going to assume, just because I'm comfortable with that. That's how I grew up. I grew up with that definition. The book doesn't. The book distinguishes between them. So be careful. I'm going to assume, because in algebra, in algebraic situations, which we're going to be facing for the next year, me and you, if you're in the next semester class, all of the rings we ever think about have a 1, have a multiplicative identity. So I'm going to assume rings always have multiplicative 1s. Okay. So now, one of the great upshots, one of the great benefits of having this convention is that we should have a separate name for things like 2z, where it's got everything except multiplicative 1. So we have a separate name. There's a funny separate name for ring minus 4. Okay? I hope you know what I mean. It's a rung. It's spelled RNG. Because see, you've removed the identity. You take it out and you just get rung. Kind of like rung, but rung. So this is a rung, but not a ring. Okay? This is real math, folks. This is real content, important. It's not, all right? So every time we say, it's just a convention. We will say rings have a 1, okay? And then the other things are called rungs. Can we call it wrong? Like a wrong? That would be shots fired, AC. Okay, yes, smash time. I am back. I am back in my natural form, natural state. Okay? Awesome. Yeah, shots fired if you say wrong. That's going a bit too far. Because Kappa and these analysis people and all these, just these people, even-minded people. Who studies 2Z? What a joke. Okay. All right. Okay, yeah. Go talk to Smash Time fools about L1. All right. Put that stuff. We don't talk about L1 here. Okay, L2, L3 halves, Sobolev, whatever. Go talk to Smash Time about these things. Okay, good. All right. Great. So that's what a ring is. And now you go back to all the examples, class. And remember, every time a new concept in a math class shows up, it is your responsibility to bulk up the bag of examples that you can test statements against. This thing. This is the most primitive ring, the first example that the definition is kind of based off of. I do want to emphasize one thing. There's a subtle difference, actually not very subtle, between this and this. Okay, and Okay, these are purple. This is green. This is purple. This is purple. This is purple. This is green. And this is purple. This is purple. And the what I did there was distinguish between commutative rings and non-commutative rings. Okay, so just like there are non-commutative rings and then there are commutative rings. Non-commutative and commutative is talking about the multiplication rule. Notice nowhere here did we say that multiplying is commutative. Nowhere, right? So there's some interesting thing to note there. We do enforce associativity in the multiplication rule because it tells you how to multiply any number of elements in any kind of clustering. Not in any order, but any pairwise clustering. Okay, so that's an important axiom, but commutativity is not in there. Great. So you understand this. Oh, wait. Okay, there's some big debate. Let's see what's happening here. What are they going to do? Triangle inequality us to death? Exactly. That's all they can do, right? And holder inequality. They're just going to triangle and holder us. Yeah, please. Okay. So yeah, we're going to stand by this. Rings have unity. And in the book, you'll see the phrase, let R be a ring with unity. They are just saying ring for us. Okay. Good. So now what do you do now? First steps. So first steps. First things you try to prove are like the similar first steps in group theory. I think I called them baby theorems back then. Like you show that the one element is unique. In a ring. Where we assume there's a unity element. The multiplicative identity element okay, and the way you do that is you multiply two of them together. Pretend there are two. And then you just stare at this. Okay, and you get 1 equals 1 prime. Great. So that sort of thing happens. You get multiplicative identity is unique. The zero element is unique. All right. You get other things. So, instead of writing, so this is notation. If A is any element in the ring, we write minus A will denote the additive inverse. Remember, the ring with the plus operation is a group. The ring with the multiplication operation, not a group, as we will see shortly. Like, never. Okay. Okay, so we'll denote the additive inverse of A. And also, A minus B, when we write this, what we mean is A plus negative B. That's what we mean when we say A minus B. All right, so then baby theorem. What happens when you ring multiply a number by -1? Have you ever thought about that? Well, this baby theorem tells you. -1 times A is negative A. Sorry, is minus A. Thank you, Frightened Swan, for joining us, and 000 and Frosty. Wonderful, welcome. So there's a theorem. This is a theorem. Have you ever wondered what multiplication by -1 does in an arbitrary ring? All of them conceivable. Well, it just does additive inverse. Cool. So how do you prove this? I mean, you should do it. You should prove this, but you begin like this. One plus its additive inverse is 0. I just added an element with its inverse in the group law. Okay, so that's true. And then you... Wait, hold on. Hold on. I did something wrong here. Okay, before I do this baby theorem. Hold on. Hold on. Technical difficulty. We need a preliminary baby lemma. We need a baby lemma first. Baby lemma. 0 times anything is 0. Okay, that is the first ingredient, and then we'll go back to the baby theorem. Okay, hold on. Okay, let's prove this. Okay, how do you prove this? You prove it like this. You start with 0 plus 0 equals 0. Yes, 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 yes. This is what you start with. I'm getting it now. These are incredibly difficult. Very challenging. For me, they're challenging. Okay, this is true. It's the this is in the group structure. Identity plus identity is identity in the group theory. Okay, that's true. So then, multiply both sides by A. Okay, so that's true. Distributive law. Group cancellation. Group cancellation. Plus is a group. Group cancellation. First try. First try. First try. You get it? Done. QED. Done with baby. Challenging baby lemma. Okay. Did I come up with this 0 plus 0 equals 0 trick? No. I learned it from a book. I read it. Okay. Now, but I had to remember it. It's really challenging. Okay, now we go back to the baby theorem. I know it's 10:16. Let's just end on this baby theorem note. Finish it up. Okay, -1 times a equals -a. Proof. 1 plus -1 is 0. Now I'll continue with the proof. So, continue. We know 1 plus -1 is 0. Multiply both sides by a. On the right, I suppose. Not gonna matter, but let me just be all right. Let me be correct and everything. Oh. Also, a times 0 equals 0 too. You do that one. Okay. Oh no, okay. I think, whatever. 0 times a is this. Okay. So then you do, this is 0 by lemma. Then this, distributive, and now 1 times a is a. And so this element, this is the additive inverse of a, which is what we wanted to, show. All right, so the first baby simple facts about what's true in all rings. A little bit challenging, I would say. A little bit tricky to figure them out, but you're kind of used to them from what you've experienced in every single example you've ever studied. The point of these is just to tell you, yeah, it continues to hold in super generality, these kinds of little facts. But what I'll do next time, on Monday, what we'll investigate is if a times b equals 0, does a or b equal 0? You're tempted to do this kind of thing when you're doing algebra in middle school. Like solving some equation, factor it, and you set each factor to 0. That's the kind of thing that you might say, oh yeah, that sounds reasonable to hold in all rings, but it's not. And so some things hold quite generally, like these baby facts. -1 times an element is the negative, is minus the element. 0 times anything is 0. However, the dream, fantasy, general facts that you wish to hold don't always hold. And this is probably one of the first little things you would hope to hold in full generality but it doesn't, and we'll discuss this condition next time. Rings of integers and non-integers. Wait, what? It's an integral domain. It's called a domain or an integral domain. That's right. Oh, yeah. I guess kappa, that's called integral? Maybe the integer versus non-integer. I don't even know how to say that. Oh, integral. Yeah, so that must be the word integral. Yeah, that's what we say too. Integral. It's an integral domain. Yeah. Okay, great. So it's 10:20. So I have to go learn alternating series test. That's right. Alternating series. So I do intend to have office hours at 5, but I'll just be messing around on doing some work related stuff, and I'll look at Discord if there's any questions. I understand that most of the classes has done all numbers up until 168 except for 144. So I can help you with 144 and try it out myself if you'd like to see how I do it. But I suspect that outside of that, y'all probably don't have too many questions. So I'll just kind of do other work related stuff from 5 to 6, and then answer. And then if the calculus students come at 6, I'll answer whatever questions they have. But it won't really be a very enlightening office hours, so you shouldn't. So the weirdos shouldn't show up. The book also has some tips. Where does it? Does the book compile all the techniques at some point? I haven't checked. That would, the way we're doing it in the Tricks of the Trade channel. Chapter 25 is our homework exercise. What? Well, that's great. Good for chapter 25. Up through 200. Nice. That's incredible. Okay, that's good. Well, then I guess I don't have to talk about that. All right. Okay. So let's wind this thing down. Let's do credits. Who do I credit today? Who came up with the concept of a ring? Sorry, who came up with the first? Okay, the ancients came up with it, I guess. But let's see. Let's see who to credit mathematically. Wikipedia. Oh, I can just type ring. Ring security systems. Definition. Okay. Who first? History. The study of rings originated from the theory of polynomial rings, algebraic geometry, and the theory of algebraic integers. So take your L1 norm and just shove it. Dedekind. Define the concept of the ring of integers of a number field. I'll just say define the concept of a ring. Great. But Dedekind did not use the term ring and did not define the concept of a ring in a general setting. Crap. Okay, so who did? Hilbert. Hilbert. Ooh, this is getting closer to the kappa. Okay, it's still rings of integers. Okay, in 1892, Hilbert was thinking about rings of integers. Okay. Frankel and Emmy Noether. Okay, so these are the people that are historically. Emmy Noether didn't. Emmy Noether did not require a 1. Frankel, my dear, I don't give a damn. What kind of comment is that? Okay, we are putting a 1 in our rings class, even though the greats did not do that. The all-time mega champion superlords apparently didn't. But then there's some more recent people who did. Okay? It's changing. It's changing with the times. What a controversy. It's a heated debate. Okay. Great. So that's who we credit, and then of course right beneath them is Crow. Okay, right under that. Yeah. And then Kappa. Smash Time was here. Great luminary. Okay, algebraically challenged. Tackling all the trolls in the chat while I'm busy talking about rungs and rings. Oh yeah, yeah, they are. That's what they're doing. Yeah, look at that. Yeah. No, he's not a troll. He's not a troll. Definitely not a troll. Be careful there, Crow. Be careful. Oh wait, you're a subscriber? Okay, you're fine. I was gonna threaten you with a ban, but you know, Ash. Gauss getting the credits for Z join I. Well, Gauss is just always Gauss is up here. So, if we're gonna start including Gauss, it's just game over. Oh, Gaub. Mm-hmm. Is it 2? Okay. It's Gaub. Okay. Okay. Awesome. Who else goes in here? Who else am I missing? I'm missing a bunch. Oh, AI was here. All these people were here. AI. RDL was in here? Maybe not. Will was in here. Who is WRR? R. My precious. Okay, that's pretty much it. These are the... You weren't here? Okay, Hangs, mate. AI. Right here. I just call him AI. Because what is that? What is that name? Like, what? He just spammed just on the keyboard. And then he spammed another sequence of letters in the explanation. It's this other. And then he went like this. Yeah, exactly. It's a circular definition. Wow, really? How do you pronounce it, AI? How do you pronounce it? No, it's AI, Kappa, AI. You pronounce it like it's spelled. Aitausuk. Aitausuk. Where's the accent? Where's the... Aitausuk. Aitausuk. Aitasuk. Alright, I'll try to say it. Now that I know, it wasn't random spam. Aitasuk. Aitausuk. 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 Oh man. Alright, now I'm gonna say that. I'm gonna try it. It means one who yawns, crow. Which is, you know, I mean, that's the kind of class I have. I mean, that's what I deserve. Oh my god, 10:35? I don't know what an alternating series is. I have to go. Okay, let's go. You see, I have some obligations. Yesterday, Booyah came in and, you know, dumped an obligation in my chat. So we have to go say hi to Booyah. So let's go do that. Then what is... Kappa. Wait, Kappa. Hey, Kappa. How was your lawn mowing? It was great. But Kappa, everybody, have you noticed? Yeah. AC? Exactly. Exactly. Kappa is never seen at the same time as the fake wife account. Have you seen that? Have you seen it? You've never seen it. No, but the fake wife doesn't make like I am very smart comments. You know? They're not like, you know, how Kappa is sometimes. So I don't know. I would think that, yeah. The fake wife is way more like chill and like relaxed and not trying to impress all the time. So I'm a little bit, yeah. Yeah, exactly, Hangsmate in one. Yeah, that's the thing. Exactly. He knows, like, what's my defining feature? I'm very smart. So what do I have to do to disguise myself? Just chill out and not try to impress all the time. See, that's the thing. It's difficult now. Huh. Kappa. Kappa's so great. Kappa's wonderful. Kappa's an honorary student. Alright. Takes all this abuse. But then continues to add quality to the community. With his L1 norm and his L2 norm. Just watch. Tomorrow L2 norm. And then L3. Amazing. Oh, hey, Professor Peter. I'm about to leave. About to leave. Wanna be it. Thanks for following. Perfect. Yes, yes. Perfect. Hey, you made it. Hey, you made it. And I have your exact type of green here. Big bad moderator, Professor Peter. Math professor. Also teaching Calc 2. We're competing. Yeah. The only reason I have this shade of green is because I have to write your color properly. No joke. That's why it's here. And same with the orange for Smash Time Fools. Yeah. Anyway. Yeah, Crow, your name is... Yeah. Like, in my chat, it doesn't even show up. So, like, it's just blank, because it's like... It blends in with the background. But I know it's you, because of the quality of the comments. I can infer it. Oh, credits. These people are the parents of ring theory. Dedekind, Hilbert, Frankel. Another. And then Crow comes right afterwards for cash money reasons. And then Kappa for, you know, all of Kappa's great contributions to the channel. AI Will. Usual suspects. Students, former students, friends. Hangsmate. We don't really talk about them much. Alright, so here's your Smasher. What about Smasher? Who is this Smasher? Kind of not sure who that is, but they seem to keep spamming stuff, so yeah, you got noticed. There you go. That's your dopamine for today, and enjoy it. Now, who are we gonna go visit? We haven't visited someone in a while. I need to increase my standing in the world. We need to choose the person wisely. Oh yeah, Booyah. We need to go pay back Booyah for coming to visit us. That's how streaming works. Who else is on? I don't know how to check who's on. Is Gath on? But Gath doesn't allow visitors. Let's go Booyah. Booyah, go learn about financial mathematics. How to finance yourselves. It's maths. It's maths. Wait, it's Melko? Melko's on? Kind of early for Melko, no? No Melko. Yeah, he's not on, I think. Yeah, Booyah. Go be with Booyah. Because of obligations. Social obligations. Spam social obligation when you raid Booyah. I'm just gonna go in, dip out, because I gotta learn what I'm teaching today. That's what professors do. They just cram right before the class, and they kind of wing it mostly. All right, social obligation raid. Okay. Okay. Go ahead and social obligation. Social obligation raid. End this stream.